of gln over f. And what does this mean? It means that it breaks up as a tensor product of representations of gln over the corresponding local completions of f at the various finite places and the infinite place, and satisfying some conditions. And the example I'd like to give is that suppose f is a CM field, then the condition that is completely essential is that if you look at the dual representation, this is isomorphic to the representation twisted by its complex conjugate. Then associated to such an automorphic representation, you can find for each prime L a Galois representation, rho L, which goes from the absolute Galois group of F to gln of QL bar. And the construction of such a Galois representation is non-trivial if you assume, so if you expect that these local representations, pi v, correspond in some way to the restrictions of the Galois representation rho L to the decomposition groups at the various places. And a natural such correspondence is given by the local Langlands map. So this is a setup from David's talk. And we saw a simple example for n is equal to 1, where the automorphic representation was given by just a Hecke character going from the Adels and invariant under the rationals to C star, with the property that when x is a real number, then the value of the character is just x to the power n. And in this case, n is called the weight. And associated to this, we saw that you could find a Galois representation going to QL bar star. And whenever you looked at ZL star, the map was simply x goes to x to the power n times something of finite order. And this was called de Rham. But you can also say that if the character, when restricted to ZL star, is equal to 1, so in other words, it's an unramified character at L, then in fact, RL on ZL star is simply x goes to x to the n. And this is what is called crystalline. All right, so I'd like to bring your attention back to the original theorem, which said that associated to these special automorphic representations with this condition and some other conditions, you can associate a Galois representation. What if want to remove the condition that the dual is isomorphic to the complex conjugate? Then, unfortunately, the entire mechanism the entire machine that allowed one to solve this problem no longer works, and you have to be much, much less ambitious in terms of what you can prove. And the theorem is the following. Well, let me erase this. The theorem, which is due to a very long list of people, but it was designed by Richard Taylor, the entire project, and is the following. Suppose n is equal to 2, and f is just a quadratic imaginary extension of q. And suppose again that pi is cuspidal, it's regular algebraic, automorphic representation of GL2 over AF. But you no longer assume that the dual is isomorphic to the complex conjugate. However, assume instead that when you look at the central character, this is just equal to the twist by complex conjugation. Then the result is that there exists a Galois representation, rho L, going from the absolute Galois group of F to GL2 QL bar. And, well, there exists a finite set of places S of F such that, well, let me say it like this. Well, when L is not in S, and V does not divide L, then the Galois representation, restricted to the decomposition group at V, is unramified. And this is, in fact, the content of basically this correspondence. It corresponds to, when I look at pi, the local component at V. The second one is when L is not in S, but V divides L, then rho L restricted to the decomposition group at V is crystalline. And I remind you that this is the corresponding term in the case n is equal to 1, to where the finite order character was trivial. So it's crystalline, assuming a technical condition. On pi at V. And this technical condition is that if I look at the roots of a Hecke polynomial, they are going to be distinct. And now, of course, you also expect that equivalence of, similar theorems in this case happen when L is inside the set S. And let me just say that when L is in S and V divides L, you expect this Galois representation to be the ROM. But of course, this, it's not yet proven. I've worked on the second part here. And so let me make good on my promise to explain what the connection is between this theorem, which is a priori just constructing Galois representations, and the title of my talk, meaning families.
Can I
yes?
just clarify, when you say theorem of Richard-Taylor ... I mean, somehow part 2 is a theorem of U, right? You didn't put your name.
Yes, that's the content of my thesis. But the construct, so Richard Taylor and a long list of other people, Michael Harris, Sudri, Hartsosh, Berger, Weishauer, anyway, a very long list of people constructed these Galois representations and showed the first part. And well, anyway, so I'm going to explain to you how to think about the second problem. And I'm going to continue on that board. So, all right, I'm going to phrase it like this. The reason all this theory is hard is that when you look at GLN over some field F, there is no convenient geometry unless n is equal to 2 and f is totally real. So basically, there's only one way in which we can construct Galois representations associated to automorphic forms, and that is by looking at a piece of a cohomology of some algebraic variety. And there is no such nice algebraic variety unless n is 2 and f is totally real. So, well, rather than giving you an idea of why it's hard, let me give you an idea of why it's not hard when n is 2 and f is q, for example. N is 2, f is q. And let's say that pi is the automorphic representation associated to a modular form, a classical modular form of weight 2. So such a modular form can be just written f of q is sum of a n q to the n. And let's assume that it's a cusp form. So from n is equal to 1 to infinity. And let's assume that the ANs are actually rational. Then there exists a natural elliptic curve, E defined over Q, in some sense associated to F. So now let's look at this type of a theorem. For the second part, well, let's start with the third part. E is an elliptic curve. That means that it's smooth over QL for any prime L. Then simply by looking at geometry, you get that the local Galois representation is de Rham. But the elliptic curve will have will have good reduction at almost all prime numbers. So outside a finite set of places, the elliptic curve will be smooth over ZL, not only over QL. And again, by general theorems in geometry, you get that the Galois representation is crystalline. But of course, essential here is the existence of such an algebraic geometric object.
I have a question. When you say there is no convenient geometry, you really mean there's no known convenient geometry, is that right? Or do you have an actual reason why there can't be?
I'm saying that there's no Shimura variety associated to this reduction.
By methods we know.
Yes.
Right.
All right, so the setup is we are on GL2 over F, which is a quadratic imaginary field. There's no nice geometry. And I have this pi, which is regular. And you can transfer it to a situation where there is nice geometry. And this nice geometry, well, for those of you who are familiar with number theory, it's GSP4 over the rational numbers. So, I've just finished graduate school, so my experience in math is very brief. But I've learned that, much like in economics, there's no free lunch. So, you go from no nice geometry to nice geometry, but you lose something. And what you lose is you end up with an automorphic representation, which is not regular. And then, basically, you have to hope for that whatever difficulty you traded the original one for is more amenable to your methods. So how do you deal with automorphic representations which are not regular? Well, the prototypical example is that of F, a classical modular form of weight 1. And in this case, the Galois representations were constructed by Deline and Serre. And in fact, the underlying idea of their method generalizes. What's that? Yes, yes. Classical. So what is their idea? Well, the point is that there exists an Eisenstein series of weight p minus 1, which is congruent to 1 modulo p. That means that I start with f, which is of weight 1. This is congruent to f times e to the p to the n modulo p to the n. And this will have weight 1 plus p minus 1 times p to the n. So you find congruences between a non-regular form and something which is regular. And by this method, you get Galois representations, rho, associated to f, which is congruent to Galois representations rho n modulo p to the n. And now suppose that that for the regular rho n, and here I mean that these Galois representations come from regular modular forms, you know local properties. For example, crystallinity. Then the question is, when can you deduce the same for rho? Or in fact, when can you deduce any local properties for the Galois representation rho? And the answer, there are in fact two answers. The first situation is if the weights of rho n are bounded, independent of n, then you can deduce from rho n crystalline, you can deduce that rho is crystalline. So this kind of a theorem was conjectured by Fontaine and proved by, again, many people, starting with himself and ending with Tong Liu. But of course, if we look at our case here, the weight is going to be 1 plus p minus 1 times p to the n, and this is, of course, unbounded. The second circumstance in which you can get any information about rho at in the local representation is if can interpolate the congruences rho n congruent to rho to a family. And here by family, I mean a p-adic family. Then, and here I'm going to put in parentheses, using the technical conditions, you can deduce that rho is in fact crystalline. So then, as you can see, the ideas up to this point have already existed in the literature. And then if you wanted to prove something about the crystallinity of the Galois representation at P, the only thing that you had to do is create such an interpolation. And that is the body of the proof. Now, the only comment I'd like to make is that this technical condition is essential. So if the roots of the Hecke polynomial are equal, then there's no way using such an interpolation to get crystallinity, simply because you can construct counterexamples. So in order to finish the proof in the remaining case, you'd need some kind of a combination between the two. But that sounds like a very daunting problem. And so I'd like to leave it at that.